currently we are studying this independent event. So we studied the conditional probability. Observing the event B, assuming that the event A already happened already. So that corresponds to So if we know A already happened, and then our entire universe will become this part, right? So we don't consider the rest of them, right? Because we know A already happened. Okay, and then P of D given A means, treating this part as our new entire universe or the entire set. What is the probability of observing the event B? Okay, so that way we understood this as some kind of ratio between these two areas. Right? So that was our definition or intuitive understanding of conditional probability. And then in this slide, if the two events are independent, and then we have to satisfy this equation, but by the fact that this guy or this guy is the same thing between this and this, it's just a notation difference. And then this guy is written by this, and then if we equate it, and then we can cancel it, and then it means P of an A is the same as P of A given B. And then also, if we use this, then we obtain this equation. Okay, and then let's look at this example, and then using this example, let's try to understand the independent situation. So let's consider P of maybe the last thing first. P of CD. So it's a used car example. And then what is the P probability of having a CD player? When picking up a used car randomly, then it is this guy, 0.4, right? So without knowing any other information, just purely randomly choose, by choosing a used car, 40% of them will have CD player. And then if having a CD player and also having an airbag are independent, and then this guy should be this, right? And so then we obtained this already. Then what about this P of CD given airbag? What is this probability? Okay, so we assume that airbag already happened, right? And then we only consider between these two situations. And then considering this as our entire universe or entire set, and then we consider having the CD player within this universe. And so 0.2, 0.5, So adding these two, and then use it as a denominator, and then 0.2, which is 2/7, right? Okay, so these two are not the same, not equal, and so they are not linearly dependent. Okay, and then let's just relate or match each of these cells into our Venn diagram or this set representation. So this is considering all the possible cases, which is our sample space, right? So sample space is our universe, and then P of airbag is like this, airbag, and the rest of them is no airbag, right? And then we consider the CD player like, let's see, let me use a different color. The event of having a CD player as this. Okay, then this part is the case of having both airbag and CD. And so here, right? And then this part is what? This part. No. So yeah, it is right? So this part is corresponding to this, right? And so this part is 0.2, 0.5. Okay, and then similarly, this part is 0.2 and 0.1. And then altogether, if we sum them, all these, sum all those four probabilities, and then it will be equal to 1. Okay, and then let's consider the ratio for this one. This one is the ratio of this part, right, of having a CD player out of the entire universe. So our entire universe is 1, then that part is 0.4, right? So this is corresponding to this value. And then as I explained last time, this ratio or this probability should be equal, or they should remain the same when considering this situation. So this situation is, so we only consider this airbag case, which means now our universe is this part, right? And then out of this small universe, what is the portion of having a CD player, which is the ratio between these two, right? So certainly those two ratios, when treating this as our universe and also treating this as our universe, so those two probabilities are different, and so this one is the case of dependent case, statistically dependent case. Okay, and then let's consider, let's see. Let's consider the independent case, and then those two ratios will be the same, which means the entire area to this area, this ratio is the same as the ratio between this and this, okay? And then also, if that ratio remains the same, and then what about this other case? What about this other case? So other case means, so the remaining part, or the opposite side, will also have the same ratio, okay? Because we have 1, and then 1, the entire universe was 1, and then it decreased to 0.7, and then the remaining one is 0.3, okay? And then this is a small circle was 0.4, and then 1 to the 0.4, and then so this ratio should be the same, and then this guy should be this value, right? So if that is the true, and then this is the case of a independent case, and then let's consider this part, which is the entire universe as 0.3, and then in this case it will be this probability, okay? So this ratio, if this ratio remains the same in this case, which is P of CD, and this guy is P of CD given airbag, and then what is this? So this is CD given no airbag, okay? So if these two are the same. And then the third one is automatically the same. So in that case, these two should be the same. And then also it means this guy also should be the same. Okay, so this is a statistical independence. And then if we have a multiple event that we have to consider whether they are, whether they are independent or not, and then we only considered like 2 events. But what if we have more than 2 events? And then we should satisfy all the possible independence equations. So we consider all the pairwise cases. Okay. So if we have a 5 event, and then if we want to see if all the 5s are independent, and then we pick up every possible pair of these 2 out of 5. Okay. So in that case, we will have in total 10 cases. Okay. Ignoring the order. And then we have to check for each of these 10 cases. We have to see if this is true. Okay. And then we also consider like a triple. Okay. So we pick up all the possible 3s out of 5, and then have to satisfy the equations corresponding to every possible triple out of 5 events. And so on. Okay. So this seems to be quite strict, but that is the condition for independence for among the multiple events, which are more than 2 events. Any questions? Okay, then the next chapter is about random variable and expectation. So what is the random variable? Random variable is a function, okay? Some function. So function should have some x value, and then it is mapped to some y value, okay? And then in the case of an x value, it is all the possible events defined in our sample space. So if we have a coin flip, then all the possible events are head or tail. Okay? And then each of these events should be mapped to a real value. Okay? Real value. Some real value, which means some number. Okay? So this kind of transformation is called a random variable. Okay? Then it can be a discrete or continuous, because the possible outputs in the place of y part, it can be just continuous real values, or the integer, or maybe some other discrete variables. So if we roll a dice twice, so we will have all the events like ranging from 1, 1, which is the smallest dice pair, and then 6, 6, which are the largest one. And then each of them are our individual events, right? Then this guy is mapped to some value, and suppose that mapping is defined as the sum of these 2 values. Okay, sum of these 2 values, and then it will be mapped into 2. Okay, so this is our x, and this is our y, and then 1, 2 will be mapped into 3, but at the same time 2, 1 will be also mapped to 3, right? So that way each of different events will be, can be mapped to the same value in our random variable. And then, we can consider the probability of observing this random variable as 2. So let's call this is a maybe dice, and or our experiment, for example. And then experiment output is mapped into the random variable x that we call. Then if x is 3, and then we can consider the probability of x being 3 by summing up the probability of each of these corresponding events. Okay, so that way we can define this probability corresponding to a particular value of our random variable. And then, considering all the possible probability value for all the different y values. So in this case, y value can range from 2 to 12, right? And so this guy will have a certain certain probability value of 1/36, right? Because it's 1/6 times 1/6, because we only have just a single case. And what about this? This one will be 2/36. Okay. Yep. So that way we can consider these probability values for all the possible random variable output. Okay. So that is called a probability distribution. Okay. This is the example that we saw. And then let's study this cumulative distribution function. So this is another type of a probability kind of function. So we have a random variable x, and then we consider the probability of observing this random variable x being equal to or less than a particular value. Okay, and then so the reason for being able to write that kind of thing, or x being equal to or less than a certain value. So for example, in this case, in this dice case, what is the probability of x being equal to or less than 3? And then we have to simply sum them up, sum these two values up, right? But one thing to note is, if it was like a sequence of or a pair of coin flip, then it will be h, 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 t, t, h, and so on, right? And then inherently they don't have any order because they are each specific event, right? Each individual event. So they don't have, they are not mapped into a certain number yet. But the random variable is actually mapping each of these cases into some number. And then once mapped to these numbers, and then that's when you can now perform this kind of comparison between these numbers. Okay? So it's like we are lining up in a particular order among all the possible events. Okay? So that is a practical kind of meaning of this random variable. Okay? So once mapping those events into some number, that is a comparable. And then now we can represent this inequality and then consider its probability. Okay, and then this probability is called a cumulative distribution function. Okay, so for each of these probability, so this f5 is the random variable x is equal to or less than 5, and so we have to sum all these up, and then this cumulative distribution function will will always increase or stay the same. It will never decrease because it will be just adding up as x values become, x values increase. Okay, so that is one property. Then, we can think of this probability of x being a certain range. So initially, in this form, x should be less than or equal to a certain value x. But what about the probability of this? Then we can represent this probability by using this cumulative distribution function, which is f of b minus f of a, right? Yep. So that is the simple derivation for this. Okay. So the probability of all the possible cases of x being equal to or less than b is divided into two different cases. Okay. And then this part is simply represented by this, minus this. Okay, it's quite easy, right? Okay, and then, let me ask a few more things. What is this probability, or what is the function value of positive infinity? So it is the probability of x being equal to or less than plus infinity, which covers all the cases. And so that probability should be 1, right? Then f of an x, and thus we'll have a range of this. Now let's look at this example. And what is the probability of x exceeds 1? So it can be written as this inequality. Then it can be written as 1 minus x x being less than or equal to 1. Okay, and then this guy is our cumulative distribution function. And so we can compute this guy. Then we can just simply plug this value 1 into this given probability distribution function, and then we can compute this probability. Okay, and then now let's study this probability mass function. So mass means some chunk, or right? So okay, so in case the random variable is a discrete, so the possible values of our random variable is only a finite number. Like, the case of this, the sum of the dice value from the two dice rolling is ranging from 2, 3, and 20. So they can be just countable within a finite number. So that corresponds to discrete random variable. But in the case of continuous random variable, there are infinitely many cases that x value can have. Okay, and so in that case, what about the So we pick up the two person, and then we collect their height, and then we sum them up, or average value of these two person. In that case, that particular random variable, which is the sum of the two persons' height, that can be just can have infinitely many values. So in that case, it's a continuous random variable. Okay. And then in case of this discrete random variable, and then we can enumerate all the possible values as x1, x2, and x3, and so on. These are just a finite number. And then for those finite number, its corresponding probability can be considered, and then that probability will have non-zero value, because that is at least some possible value of our random variable. Okay, so if that probability was 0, and then it means the corresponding value of an xi will never be observed. So in the case of a dice rolling, I mean 2 times of a dice rolling and their sum, if we consider maybe 13, which is never, which is impossible case by summing up the two values from the dice. Okay, so in this case, we do not count this guy into these possible values or the list of possible values. Okay, and then now we understand this is strictly positive value. Then for all the other values, it should be 0, and then their sum should be just 1. Yeah. Okay. Then maybe I explained a little bit in a wrong manner. So the discrete random variable is not the one that we can count. It's a total number. It's just a non-continuous one. So in the case of sum of dice rolling case, it is ranging from 2 and then 3 and 4 and so on. And so there is a gap between them. Okay, so there is no possible cases like 2.1 or 2.05 and so on. So those are not possible values. So in this case, where we have a particular interval between the two possible values of our random variable, in that case, we call that as discrete random variable, which is like not continuous. Okay, so that way, the possible number, the possible values of our random variable can be infinite number. Okay, but they have some interval among these possible cases. Okay, and then the cumulative distribution function is represented by this. It is just like this guy. So this is P of x is xi or x1, for example, and x1 is 2 in this case. P of x is x2, then x2 is 3. And then this guy, or f of an x, or our cumulative distribution function, is simply summing all these up, right? So such a summation is represented by this. Okay, and then let's consider this case where we have 3 possible values of our random variable, and then their corresponding probability are these values. And then of course they will be summing up to 1. And then this will be corresponding probability mass function. Okay, and then this guy is cumulative distribution function, or f of an x. But let's think about this edge case, those edge case. So you guys probably studied something like this, like this a filled circle, or like this blank circle, or this can be filled and this can be empty, which means from when viewing this as a function, so we have an x value and then y value is its corresponding cumulative distribution function value. Okay, and then what will be this, or the probability of x being less than or equal to 2. So that will include the case of x being exactly equal to 2, right? And so so is this true or this true? So which one is true between these two? So 1 or 2. Which one do you think is the correct one? 1 and 2. Why do you think it's 2? I'm just curious. So in this case, it means P of f of 2, which is this guy, is corresponding to 1 over 2, right? Okay, is it correct or not? So the question is, when computing this? Should we just use that value only, or should we add these two together? Should we add them or not? Because it contains the case of exactly being 2, right? So yeah, this should be added together, right? And so that exact value of 2, that is the point where we have our probability value jumps. Okay. So the first case is the correct one. So we have to have an empty circle and filled circle, empty and the filled circle. Okay, that is a property, one little property of our cumulative distribution function. Okay, then now let's consider this continuous random variable and its probability distribution. Then we can also think about the cumulative distribution function, which is f of an x. And then maybe it can be represented by some value, right? Okay, and then it is now represented by the integral, because we have infinitely many possible values of our x, because x is not just a discrete. Okay, so in that case, it is represented by this one. Okay, then this guy is called a probability density function. Okay, and then from the relationship of this integral, so this is our just typical cumulative distribution function. So that is a probability. And that probability is the is represented as an integral of some function. Okay, so we have to do the integral on that function in order to obtain the probability. So that is called a density. Okay, so it is like from some analogy. So we consider like the distance that we moved, and then we consider the velocity of velocity at each point. Okay, while we move from here to there, and then the total distance that we moved is the integral of our velocity as we go along our path. Okay, so so this is almost the exact same relationship. Okay, and from such kind of analogy, this one itself, or this small lowercase f, is not a probability itself. It's something like the velocity of a probability. Right? So our cumulative distribution function will keep increasing. So they will continuously increase, although they may stay the same, but they will never decrease, right? And so it will keep increasing until it reaches 1, which is the maximum possible value. Then we can consider that as the probability, the velocity of how fast our probabilities are increasing. Okay? So that way, the small lowercase f can be considered exactly as the velocity have a notion or constant. Okay? So again, how fast our probability is increasing, such a velocity is represented by that small, lowercase f of an x. Okay, then this one is always true. Because our velocity at a certain point was negative. It means at that point, the total probability would decrease at that specific moment, right? So our velocity can never be negative. Okay, then applying some facts that we know, like this. Then yeah, this guy will be 1, right? If we integrate it, if we do the integral on this velocity function on all the possible ranges of our random variable, okay. Then this guy is yeah, it can be represented by this one, right? Because this guy is p of x being equal to or less than b, and then this guy is the probability of p, x being equal to or less than a. Yep, and then altogether, if we combine them, then we can have this starting point at a and ending point at b, and then do the integral. And then if we set a and b equal, and then such a probability, which is this guy, then this guy is represented by this, because the a and b are the same. So yeah, so if we do the integral on the same starting and in the ending point of this velocity value, then the probability will be 0, because yeah, by definition, yeah, it is we give no x values or the length or the possible ranges to compute the integral. So in that case, regardless of any function of an f, that integral will always be 0. Okay. And then it means, yeah, intuitively that can be also considered as the probability value of observing a particular person's height as maybe 171 will be close to 0. Okay, because some student may claim that I'm exactly 171 tall, 171 centimeter tall, and so on. But if we measure exactly their height, and then it will be likely that such a height will be 171.003 and so on, right? So in practice, observing that exact value, and its probability will be 0. But still, this velocity will be non-zero. So around the 171 centimeter as a height, how many people are around there? Okay. So if we observe many people around that point, then it means the probability will rapidly increase around that point. Okay. But if we don't see many people around that specific value, around that specific value means we can consider maybe range of 171 minus 0.1 and 171 plus 0.1. So we set up those small values and then count those people that falls into this range. Then still the probability in this case will not be 0, right? Because we consider the range, and then how many people that we observe in that specific range, and then that is corresponding to the velocity of probability increase. Okay. Okay, then suppose we are given this kind of density function where we have some unknown constant. Okay, then we can utilize this kind of formula, right? And so it means the possible the x values that has a non-zero probability will only be this range, right? But still, we can consider all the ranges of the random variable from -infinity to infinity, and then we can consider the 0 probability for outside of this region, okay? X or this, okay? Yeah, so this is corresponding to the second line. But anyways, we have to satisfy this, and then this guy will be rewritten by this form, because all the range is outside of this range between 0 and 2. Yeah, it is defined by defined as 0. And then yeah, we can perform the integral of this. Yeah, let's just solve it just for fun. And 0 to 2 and dx. And then what is integral? What is the indefinite integral of this guy? Can anyone tell me? What is the number? The starting number? 2c x squared minus 2 and divided by 3c x. That's right. Then yeah, we have to do this kind of thing. Okay, so if we plug 0, and then it will all be 0. Then if we plug 2, then it will be 4. Then this guy will be 8. Yeah, and then we equate this value with 1. And then we can obtain the value of c. Okay, then this guy, yeah, you can compute integral of, yeah, it's 1 minus p of x being equal to or less than 1. Yeah, and then you can compute this guy by using this. Yeah, it is quite easy, right? Now let's consider this a jointly distributed random variable. So we have two random variables. Okay, then what will be the example? So we consider those individual events. So for example, suppose we do the coin flipping, then h, h, ht, th, tt. So we have 4 possible elementary or element events. Then let's just define the rule or the function that maps each of these as 2 numbers. Okay, so pair of numbers, and then such a pair is just a encoding h as 1, and then this guy as also 1, and then in this case 1, 0 and 0, 1 and 0, 0. Okay, so in this case, individually or each of these dimensions that we call among these pair of 2 values, okay, they are real values. Okay, so it is viewed as a pair of real values. But in the case of this event, they were not yet a number, right? That is the difference. Okay, then we can consider this kind of thing. F of x, y. In this case, the probability of these 2 events simultaneously. So it's like this guy should be satisfied, and also this also should be satisfied. So we can also consider such an event, right? Yeah, satisfying those 2 equations. And then we define the cumulative distribution function, or our probability distribution. Joint cumulative probability distribution function defined by this. And then from here, so suppose this one is defined, just like this example. So even though we didn't know C, but we were able to correctly compute C, right? By the fact that where is it? Yeah, this guy. Okay. So suppose our f of x, y is fully given. So we know fully this joint cumulative probability distribution function. Okay. Then it involves x and y, those 2 variables, and then we can compute this kind of thing, which is involving only 1 variable. Okay, the first variable and also similarly the second variable as well. Okay, so in this case, yeah, originally each of our event or this kind of random variable will have the two values, but this guy is considering, yeah, this guy carries only one variable of an x. Okay, if we consider this, that means, yeah, we allow y value as any possible values, any values will be okay. Okay, and then we have this, and then it can be written in this by using the joint cumulative distribution function. Yeah, and then similarly, yeah, for y, we can obtain this. Okay. Oops, yeah, it is a redundant slide. Okay, then now considering the discrete random variable, similar to the probability mass function, we can also think about also the same thing for the pair of random, joint random variable that has a pair of two values, right? And so, yeah, suppose the possible values of an x are these, and the possible values of an y are these. In this case, for this probability mass function is defined by the probability of x being exactly equal to this value and y being exactly equal to this value. Okay, and then in this case, similar to the process where we actually removed the other variable. Okay? So we initially given the joint cumulative distribution function involving two variables. So from there, we change it or convert it to the cumulative distribution function that involves only one variable, x and y. And then also we can do the same thing. So from this probability mass function for joint random variable, we can obtain the probability mass function of this single variable x, which means we just allow any possible y values in this pair of those two values. Okay. Okay. So in terms of an event, so this kind of event is the same as the union of x being fixed as xi, and then we consider all the possible yi values, and then its probability will be also the same thing. And then this guy is converted into this form, which is just the sum of the probability of x being fixed as xi, which is our given value here, and then we consider all the possible y values, okay, for this yj, all the yj's. And then we simply sum them up, sum these probability to obtain this value, and then more simply, this one is our probability mass function, joint probability mass function. So this guy is just added together for all the possible y values. Then here, let me ask one thing here. So from here to here, it's a little bit. Let's see. So from here to here, we changed that kind of probability of all these events, and they are combined as a union of all these events. So in general, if there are two events in our entire universe, then the probability of A, B is P of an A plus P of B minus P of A cap B, right? Or intersection of A and B, right? And then we considered all the possible y cases, right? And then we consider it's a union because we consider all these possible cases. And then it is converted into just a simple sum, which means when y has two possible cases only, maybe y is only 1 or 2. In this case, this guy means we just add these two probabilities together. So where is this term? Where is this term? Why do we not see this term, this formula, is because this guy is 0. Yeah, so it is like, so suppose x and y are the two values of a dice rolling. Then suppose x is fixed at 1. And then we consider all the possible y values, 1, 2, 3, and 4, 5, 6. Okay? And then that is corresponding to this sum. But yeah, the reason that this guy is 0 is because x is being 1 and y being 1. So this event and x is 1 and y being 2. This event, yeah, they cannot occur or happen at the same time. So they are mutually exclusive events. So if we know one of them happened and then the other for sure is not happening. Okay? So so these events are mutually exclusive one, right? And so that's why, yeah, we see this kind of equations from this to this. Okay. 딱 여기만 고침이 없네. Okay, so let's look at the example. So x is unemployment rate of of Korea, and y is economic growth rate. And then although there are many different values of our unemployment rate and this kind, but let's just suppose these two are discrete random variable. So unemployment rate is only can be one value among these three, and then this is an x and this is an y. Okay, so suppose these two are just a discrete random variable, and then these are just the probability value for each of these combinations. Okay, so our event is unemployment rate is 3%, and the economic growth rate is 20%, and its corresponding probability is 0.3. Okay, and then from this table, let's look at the last column and last row, which is called this marginal probability or marginal distribution. And marginal means this guy is called a marginal distribution. So even though our event has the form of the combinations of these two, x and y, but we just want to ignore y, and then we only we want to focus only on x, and then what will be the probability value of x being 3%, 5%, and 10%, and then simply we just sum all the possible y values and their corresponding probabilities, probability values. Then it will be this value and this value and this value. And that way, from this full information, so this full information was given by this, and then we can obtain the probability mass function or probability distribution over only x value or y value. Okay. So those two probabilities are probability distributions are called this kind of marginal probability. It's a marginal probability, and I wonder why it is called a marginal probability, because the term marginal is used in many different ways, and so yeah, the meaning doesn't seem to make much sense to me. So someone said that this marginal distribution is like in this kind of table thing. This marginal distribution is usually written at the very right end or at the very bottom end, right? So that is called kind of marginal, which is a marginal means like a corner kind of thing. Okay. Okay. So in the case of a continuous random variable, yeah, we can easily extend what we learned. Yeah, in the previous discrete random variable case. Okay, and then now, yeah, this guy is like x being greater than or equal to a and y being greater than or equal to b. So we consider this kind of event and its corresponding probability, and that is defined by our cumulative, jointly cumulative distribution function f of a comma b. And this guy is defined by the integral. So we have a double integral here. Then we have this kind of velocity function, which is our probability density function. And then we compute this double integral, and then we obtain the probability of this guy. Yeah, and then if we take the derivative, and then this guy is a like a double derivative of the original joint cumulative distribution function. Okay, and then if we consider this a marginal probability value, so we ignore y value here, and then we can consider all the possible y values, and then this double integral, one of these double integral, will be written by this in this form, which is corresponding to this guy is paired with the dy, right? So for y, we take the integral of all the possible y values. Then this. Okay. Any questions so far? It is quite easy. I totally understand that. I need to teach them. I cannot skip on my own. Okay, but in the later classes, I think we will see some interesting or some non-trivial parts that we can study. Okay, and then now consider this independent random variable. Then the two random variables are independent if their probability is decomposed into this nice multiplication of these two, or product of these two, right? And then this guy, in order to just consider our cumulative distribution function, because our cumulative distribution function, which is f of a comma b, right? So this was by definition our starting point. So we started from that cumulative distribution function corresponding to this probability, and then if the two variables, or x and y, are independent, and then we can decompose each of these probability and their product. Okay, and then this guy is again a marginal distribution or marginal probability. Okay, and then this guy is again the cumulative distribution function, but it is the marginal one that involves only the variable x, right? Not y. So here again we consider all the possible y values. Okay. then we simply represent it as a sum, the product of these two. Okay. Yeah, in the case of a discrete random variable, and then we consider the probability mass function. Okay, so the joint probability mass function, which is the probability of x being x, small x, y being small y. Okay, it is just represented as the product of these two. Okay. And then also, from this equation, where we consider cumulative distribution function or the probability mass function, and then back to this continuous random variable case, where we start with this cumulative distribution function. We can consider its a velocity function, which is called a density function, right? And then in the case of density function, this density can also be decomposed into the two marginal density. Okay, so you can easily prove that, and you can also understand it intuitively. So so for any point of x and y, for possible values of these two variables, okay, for any point, so this guy should be decomposed into that, and then in that case, this is true only when this velocity function can be decomposed into two. Okay, so let's skip the proof here. Then look at the example. So suppose we are given two random variables x and y that are independent. Okay, and then x and y both are having this density function. So these are marginal density functions. And what about the velocity function or the density function at a particular x value and y value? In that case, it is represented by this, right? And then again, don't be confused. Where is y? So y will take the same form because it says the common density function are given for x and both x and y. So we are simply taking the product between these two functions. That will be our joint density function. And then so that is the basic property. But the question here in this example is that we have to find this density function of the new random variable or new random variable of this x divided by y. Okay, so the ratio between x and y. Okay, then let's start with this cumulative distribution function. And first of all, this guy is a single random variable, right? Just one number, right? So it's not joint one, although it is a function of two different random variables. But as it is, this guy will be a particular scalar, right? X is 1 and y is maybe 3, and then x over y will be simply 1 over 3, which is just a scalar value. Okay, and so let's consider this cumulative distribution function, which is this guy, and this guy is represented by this being equal to or greater than, less than a, and its probability. Okay, then we take the double integral, okay, and then consider all the possible regions of x comma y that satisfies this. Okay, Okay, and then yeah, this guy, since it is represented as a independent one, it can be decomposed into these two things, right? So this guy, and then of course, x and y are only defined for these positive values. Otherwise, the density function is defined by 0, right? Because that is the given information from this example. Okay, then to represent this guy, we can do this guy, and then you can think about this as a kind of double for loop. So we consider all the possible x value, okay, and then for loop ends here, and then inside of it, we have another for loop, okay, nested for loop, and y should be so from here it is ya, and y should be x over a, right? Okay, and then sorry, in this example they put y here as a outer loop, okay, and then we consider all the possible y values, and then for a particular y value, what is the x value that we need to satisfy this kind of thing, okay? And this thing, x should be all the values that satisfies this guy, okay? So this integral corresponding to y is corresponding to this for loop, and then this guy is corresponding to this, and then this x is ranging from 0 from the definition of this, and then it can go up to this a times a, because x should be less than or equal to y times a, or a times y. Okay, so we can compute this integral. It's a little bit tricky problem, but it's doable. And then if we evaluate all these integral things, and then we obtain this. And then by taking the derivative, because that is our cumulative distribution function, then if we take the derivative of it, then we obtain the density or the velocity function of the new random variable of this x over y. Any questions so far? Okay. So let me give some example of this independent random variable. It seems to be connected. Okay. So let's think about some joint density function. So joint density function is just a function, and then the domain or the input value is the combination of an x comma y, right? So input is x comma y, and then the output, the density or velocity, can be mapped into some z value, right? And then for each every possible combinations of an x comma y, then we will have some function value z, which is our velocity value. Okay, and then some random shape can be shown in this form, right? So we have two x's corresponding to the two random variable x and y, and then we can consider the z value as our density value. Okay, and then the independent case means independence means the joint one, meaning the probability of x being something and y being something, and the intersection of it can be decomposed into the two, right? The product of the probability of each of them, right? And then at the same time, this independence can be viewed as the probability of observing x. It's the same as the probability of observing x given the probability of b happen or not, right? Something like that. I think kind of slide. I need to explain it in the next section. But, let's discuss it in the next class. Okay, thank you very much. 네.
이게 한꺼번에 이거 어떻게 뜯어져요?
이게 어떻게 뜯어지냐면 이게 그러니까 그 XY에 해당하는 영역이 그 영역이 지금 뭔가 우리가 이제 더블 인티그랄을 할 때 더블 적분을 두 번 할 때는 X가 뭐 0부터 3까지 그다음에 Y는 뭐 2부터 5까지 뭐 이런 식으로 X와 Y 값이 이렇게 독립적으로 이렇게 레인지가 존재했었잖아요. 근데 이거는 지금 애초에 이 식이 뭔지는 알겠죠? 그러니까 이 레이시오가 이 안쪽으로 들어와야 되는 거예요. 그러면 그냥 단순하게 그러니까 A가 3이다. A가 3이다 그러면 X는 3Y보다 작으면 이때가 이거를 만족하는 이벤트가 되겠죠. 혹은 XY의 조합이 되겠죠. 그러니까 XY의 모든 조합들에 대해서 그 어떤 density 값들이 있어서 얘네들 우리가 다 하나하나 다 모아서 적분을 하면 그게 어떤 probability 값이 되는 건데 우리가 생각하는 어떤 이벤트가 XY의 어떤 특정 값에만 해당이 되는 거예요. 그러니까 그 이벤트는 뭐냐? 두 개의 주사위를 던졌을 때 두 번째 주사위가 첫 번째 주사위보다 2배 이하가 돼야 돼. 그러면 자 1, 2, 1, 3은 되나요? 안 되나요? 안 되죠. 두 번째 게 이제 2배 이하로 돼야 돼. 2가 됐을 때는 2, 1, 2, 2, 3, 2, 4까지 되고 3은 다 되고 또 4는 다 되고 5도 다 되고 6도 다 되죠. 그러니까 그렇게 되면 이렇게 생각을 해볼 수가 있어요. 적분에 해당하는 영역이 X와 Y의 1, 2, 3, 4, 5, 6 1, 2, 3, 4, 5, 6 이 총 36개의 점 중에서 이게 약간 이렇게 잘려갖고 이 어떤 점에 해당하는 영역이 이렇게 좀 표시가 돼요. 이게 그러니까 일반적으로 디스크리트 랜덤 베리어블에서 P of X being 2, Y being 3 그러면 이게 어떻게 되느냐 이제 방금 이야기했던 1부터 6까지 이렇게 있어요. 1부터 6까지 그러면 이게 하나하나의 가능한 케이스들이고 이거에 해당하는 확률 값들이 있겠죠. 근데 뭐 주사위라는 특수한 케이스에서는 이 점들이 각각 다 36분의 1씩의 확률을 가지기는 해요. 네. 그러면 이거는 어떻게 적분을 하는 거냐 바로 2에서 이렇게 잘라 먹어요. 그리고 이 X축이고 이 Y축 3에서 이렇게 잘라 먹어요. 그래서 여기에 들어온 케이스들의 확률들의 합을 구하는 게 우리가 이제 하는 일이잖아요. 근데 조건이 이게 이렇게 안 생겼어요. 이제는 우리가 이게 어떻게 생겼냐 이제 y분의 x겠죠? 네. y분의 x가 만약에 2다 이런 식으로 주어질 거잖아요. 그러면 이거는 x가 2y보다 작거나 같다 이렇게 되는 거예요. 그러면 이게 딱 이렇게 격자로 되지가 않고 x가 1일 때는 요거 두 개 2일 때는 아까도 같이 요거 이렇게 되고 그죠? 그러니까
y는 2분의 1 x 축으로 그냥 뭐 위인가 아래
네, 그렇죠 맞아요. 그래서 이게 요렇게 되는 거예요. 요렇게. 그러면 가능한 요거는 다 이거고 이 밑에 쪽이 다 만족하는 영역이죠. 그러니까 결국은 이 네모 여기서부터 이 네모 중에서 이제 이렇게 되는 거예요. 이렇게. 그죠?
와 이거 분수였어? y분의 x였어?
네, 이거 분수였는데 그러면 뭔지 알았어요?
x와 y인 줄 알았는데
x 바 y?
네, 그냥 x, y 각각이 a보다 작은 약간 그런 거.
아, 네, 이게 분수 나누기.
그러면은 여기서 0부터 무한대, 그러니까 지금 0부터 AY라는
네.
게 지금 X,
네.
AY 이렇게 된 거라서
네.
이거가 하나 생기는 거고.
맞아요.
그 이거 하나는
그거는 이제 모든 케이스에 대해서 다 따지니까 그게 이건 거예요. 그러니까 이게 x를 하나 고정, 그러니까 저거는 이제 y를 고정을 시키고 이제 그 다음엔 그 안에서 x를 찾은 거긴 한데 뭔가 x를 고정을 시켰어요. 그러면 x가 1일 때는 가능한 게 요거 두 개죠. 그러니까 적분을 요거 두 개에서만 해야 되고 2일 때는 어떻게 되느냐? 또 요거 이 안에서 들어온 애들한테서만 해야 되죠. 3일 때는 또 그렇고, 그죠? 그러니까 요 적분 1부터 6까지 모든 값을 다 돌아가는 적분이 가장 바깥쪽이 이 적분이고요. 모든 값을 다 따지는 거. 근데 이제 0보다 커야 되니까. 그 다음엔 그 안쪽에 있는 적분이 바로 이거를 나타내는 거예요. 0부터 어디까지만 가느냐? x에 디펜던트하게 거기까지만 가도록 적분을 해야 돼요.
그러니까 지금 하나는 그냥 조건이 따로 없어서 무한대로
네.
된 거고 하나는 그 이거 때문에 생긴
맞아요.
나머지 하나.
그러면 됐나요? 그러면?
그리고 또 질문 있긴 한데.
잠깐만요. 오늘 출석이 좀 빠를 테니까 이름이 뭐죠?
김승우요.
여기 있나요?
여기 이거.
출석이요 다?
전에 와가지고.
네. 그 이름이 어떻게 돼요? What's that? 응? Do you see your picture? Let's see. Yeah. If you don't see it, then it's okay. Because we only check the subset of the students. So you may not have been called. So, yeah. 오케이? 야. 이름이 뭐예요?
함태경.
여기 있어요? 함태경? 함태경.
저 정정 그때
아, 그래요? 그럼 아마 여기 없을 것 같아요, 내 생각에. 네, 출석부를 예전 거로 한 거라 오늘.
그 혹시 그 출석 그 얼마나 됐는지 그런 거는 확인할 수 있는 방법인가요?
그러니까 결석이 얼마나 됐는지
네.
나중에 그거를 알려줄게요.
혹시 그 F 조건이나 제가 늦게 들어간 거니까
네.
다른 그 환경도 다 다르고 해가지고.
네. F 조건? F 조건은 뭐 글쎄요. 시험 다 보고 숙제 이제 낼 거 뭐 대부분 내면 이제 F는 없나 하고.
알겠습니다. 없는 거 없겠죠.
아마 나중에 들어왔으면 아마도 없을 거예요.
왠지
네, 여기서 한번 찾아보고.
출석 때문에 F를 받는 게 있어가지고 민감해서 이게.
제 결석을 해도 뭐 F를 주진 않아요.
출석
이름이 뭐예요?
일인지가
불렀어요?
있지 않나요? 똑같은 거네.
아니.
사이 똑같죠.
뭐 아마 지금
여기나 여기
그 이거 아까
네.
이게 범위가 1번까지만이라고 하셨던 거죠?
응?
그 이거 X는 2보다 작거나 같다의 확률이 1번까지만이라고 하셨죠?
1이랑 이제 2가 2까지 포함이 되는 거니까.
그럼 여기까지 아니에요?
네?
아까 여기까지라고
네.
여기까지 해야
그렇죠. 그러니까 2일 때는 그때 해당 probability mass까지 이제 더해지는 거죠.
네.
그래서 그때 점프가 일어나는 거죠. 2일 때.
네, 그러니까 그 점프한 거까지
네, 그렇죠. 한국까지니까 여기가 칠해지고 여기가 안 칠해지는 거죠.
그럼 아까 그거
내가 뭐 잘못 설명했나요, 혹시?
아니 아까
네.
질문하신 게
네.
그 1번이냐 2번이냐 물어보셨잖아요.
네.
그거는
그거는 이제 요 X축이 중요한 게 아니라 이제 그 필드 서클이 이제 위에 존재하느냐 아래에 존재하느냐 요 패턴을 물어본
그 이거
거예요.
점이 어디에
예,
존재하느냐.
그 위아래 중에.
아,
예.
그걸 몰라가지고.
아, 네. 아, 네. 지금은 좀 모호했네요, 그게. 예.
그리고 이거
네.
기호가 뭐예요?
그거는 이제 다 곱하는 거. 이제 이렇게 쓰여지는 게 시그마가 다 더하는 거이듯이 이거는 이제 다 곱하는 거를.
이걸 I 1부터 n까지 확률을 다 곱하는
네.
그 숙제에서 관련해서
네.
질문. 이거
네.
여기 그리는 거 따로 해야 된다고 하셨잖아요.
네.
이거를 다 이런 식으로 해가지고 찍어서 올려야 되는
네,
거죠.
손으로 그려서 네, 그렇게 해야지 되겠는데요.
그리고
네.
이게
네.
입시에서
네.
히스토그램을 그리라고 한 게 있는데 이게
네.
이거 표 보면은 이게 이걸 가지고 어떻게 히스토그램을 그려야 되는지 모르겠어요. 그러니까 그게 범위가 정해져 있어야 되잖아요.
네, 그거를 이제 적당히 우리가 정해서 아마 그리면
그냥
될 거예요.
적당히 정하면
네,
돼요.
네.
그리고 빈도표 같은 거 할 때요.
네.
중간에 그 수의 범위는 0부터 10일까지인데 막 만약에 중간에 7, 8, 9, 10 막 이런 게 다 하나도 없고 그러면은 그것도 표시를 해줘야 돼요? 아니면 그냥 넘어가세요? 그림 그릴 때는
그림 그릴 때는 이제 X축 이렇게 있으니까요.
그거는 그냥 0을 이렇게
네, 그렇죠.
표시만 하면
네.
되는 거예요.
그렇죠. 네.
그리고
네.
상대 빈도 안 나서 떨어지면
그거 소수점 적당히 쓰면 돼요. 네.
1 꼭 안 나와도
네. 그러니까 뭐 어떤 자잘한 아주 그 계산 이렇게 좀 차이 나는 거나 이런 거 가지고 막 점수를 깎고 그러지는 않거든요. 그래서 아마 뭐, 네. 네.
이게 그러면은
이게 조인트 이건데 요거를 이제 뭐 더블 인티그럴, 그러니까 적분 2번 하거나 뭐 이런 식으로 해서 하는데 이게 그러니까 적분을 따로따로, 그러니까 마지널 그 probability mass function을 혹은 저기 cumulative probability distribution 이렇게 따로따로 구해서 마지널을 따로따로 구해서 걔네들에 대해서 적분을 따로따로 한 다음에 이제 곱하면 된다라는 의미거든요. 네? 그게 그러니까 인디펜던트 하네. 네네네. 독립이요. 네, 그러게요. 이게 좀 이 제목을 내가 좀 잘못 쓴 것 같네요. 이게 독립일 때의 그런 거예요.
뭐 여기서
네.
접근할 때
네.
x가 a, y여서 0부터 a, y인 거잖아요.
네.
y는 왜 0부터 무한인 거예요?
그러니까 이제 y는 이제 뭐 아무거나 다 되되 그때 해당하는 x가 만족하는 그 값들을 이제 해주겠다 이런 개념이거든요.
아, y는 다 하고
네.
어차피 x는 a, y니까.
네, 그거보다 이제 작거나 같으면 되니까 네, 그런 식으로 한 거예요. 그러면 이제 저 관계식을 만족하는 모든 그 x, y의 조합을 우리가 다 따진 게 되니까.
x 범위 무한대, y 범위. 그러니까 여기서 이미 x가 a, y인 걸 해보셨으니까 y 범위는 무한이었고 y 범위 a가 정확하다.
네.
제가 군인 다음 주 저녁에
아, 그래요?
다음 주 화요일 수업을 못 나오는데 출석 되고
아, 그래요. 뭐 그러면 사유 같은 거 이렇게 뭐 증빙할 만한 거,
저녁 지금
뭐 그런 거를 보내주면 4번으로 이메일로 보내주면 네. 네.
그 랜덤 배력을 저희가 이제 펑션, 그러니까 그 실제 사건 일어나는 걸 갖다가
네.
그 숫자에다가
실수로
이제
맞추는 거죠.
그걸 대응시키는
네.
그 대응 관계를 갖다가 이제 랜덤 배력이라고 생각하는 거죠.
네.
저는 지금까지 랜덤 배력이라고 하는 게 그냥 그 숫자라고 생각해요. 근데 숫자로 이해를
이게
같은 의미인 것 같아요.
이게 약간 달라요. 그러니까 예를 들면 가위바위보에서 내가 이제 가위바위보를 해요. 그래서 내가 이길 때, 질 때, 비길 때 이 세 가지 케이스가 있잖아요. 그다음에 이거는 하나하나의 그냥 이벤트인 거예요.
네.
하나하나의 그 이제 엘리멘터리 이벤트가 되는 거고 이거 자체는 어떤 숫자는 아니죠. 근데 이제 랜덤 베리어블은 여기서 어떻게 되느냐? 이겼을 땐 내가 뭐 예를 들면 2, 비겼을 땐 1, 졌을 땐 0으로 일단 매핑을 하는 그러고 나서의 그 숫자들을 이제 랜덤 베리어블이라고 해요.
아, 그리고 그 함수를 쓰면은
네.
그 이제
함수의 y 값이
값이 랜덤 베리어블인데,
네.
근데 이제 정의에서는 펑션이라고 해서
네, 네, 그러니까 펑션 자체가 이제 정의가 맞는데 이제 펑션 아웃풋의 값을 이제 그 랜덤 베리어블이라고.
그러면 랜덤 베리어블은 펑션이라고 해도 되고 펑션 아웃풋 밸류라고 해도 되고.
네, 그러게요. 그런 거 그 두 개 중에서라면 아마 내 생각에는 펑션 아웃풋으로 정의를 하는 게 좀 더 맞을 것 같아요. 네, 펑션 밸류, 네, 펑션 자체가 아니라.
저도 지금까지 밸류라고 생각했는데 그 이제 그책그 카피 그 PPT 해주신 거거든요. 거기에 책에서도 거의
펑션이라고 돼 있어요.
펑션으로 돼 있으니까.
네, 그냥 거의 좀 이렇게 그러니까 명확한 구분이 있게 쓰는 건 아니고 네, 그런 것 같아요. 네.
아까 여기 이거 해주실 때 그러니까 이거 같지 않으니까 뭐 독립 아니다 이거 할 수 있잖아요. 그럼 당연히 그 노 에어백이랑 노시리 이것도 이제
달라지죠.
당연히 걔네도 그러니까
맞아.
한쪽이 독립이 아니면 다른 쪽도 당연히 독립이 아니잖아요.
그렇죠.
그러면은 이 아까 1대 0.4, 뭐 0.7, 0.8 이거 말씀하신 게 그 1대 0.4면 이제 전체 중에서 CD가 0.4인데 이제 0.7, 0.28이 원래 나와야 된다 이런 말씀이시죠?
네, 그게 만족이 되는
그 비율로 가야
네,
독립인 건데 실제로 구해보니까 아니니까 독립이 아니다 이렇게 말씀하시는 거예요.
근데 또 하나는 거기서 얘기한 게 세 번째 식으로 쓴 거는 그 첫 번째 그 두 개가 똑같으면 마지막 식인 그 반대쪽 있잖아요. 0.7 부분 말고 0.3 부분. 그러니까 그 여집합에 해당하는 부분에서의 상대적인 그 어떤 그 비율도 그 이벤트도 이제 똑같이 유지가 됩니다.
그러니까 이게 되면
네, 밑에 거 세 번째 식도 자동으로 된다.
그러니까 그럼 독립이 그 반대편이 독립이면 나머지 하나는 무조건 독립이고
그렇죠.
독립이 아니면 그러니까 서로 그거네요. 역도 성립을 하고
뭐 그런 셈이에요. 그러니까 이게 이런 거예요. PA가 뭐 PD가 PD 기분 A와 똑같으면 이게 두 개가 만족이 되면 PD 기분 AC도 똑같아요. 네. 이거 두 개가 되면 이거는 자동으로 따라서 이게 되고요. 이거 두 개가 다르다? 그러면 자동으로 얘랑 얘도 다른 거예요.
그러니까 이게 결국은 그 분포로 보면 같은 비율로 분포되어 있지 않으면 그 독립이 아니고 같은 비율로 똑같이 따라가면 독립이다.
맞아요. 네.
내용은 다 아는 건데 그 뭐라 해야
네.
중간중간에 좀
네.
심하게 이제는 좀